Welcome back everyone. This is part 2 of lecture 3. I shall continue lecture 3 part 2. I shall continue. In part 1 we talked about definitions, we talked about postulates, common notions and so on. So in this part 2 I'm going to state and prove some of the propositions in the first few books of elements, and specifically I will be talking about the proofs of the propositions that we will need for finally proving a Pythagorean theorem. So let me just start with proposition 1.1. By the way, if you hear proposition 47.2 or 32 or 13.5, this means that we're talking about proposition 5 of book 13. Therefore 1.1, it means proposition 1 of book 1. There are only 13 books anyway. So proposition 1.1. This proposition will use nothing that it wasn't talked about before, I mean before in part 1, so we simply are going to recycle postulates, common notions and definitions to actually give a proof of proposition 1. So proposition 1 says the following. It is possible, or we can construct an equilateral triangle on a given finite straight line. Let me just write this down. So it's proposition 1. Construct an equilateral triangle on a given finite line. On a given finite straight line. Okay, here's proof. We are given a finite straight line AB. Let me just draw that. Okay, so let's say this is our given finite line AB, and we are to construct a triangle with sides the same length as AB. So the first thing we do, we take the compass, we place the center, well, we can start with A. We place the center at A, we open the compass with radius AB and mark an arc. It's the same as if you were to draw a circle, but I'm not going to draw a circle, I just need this arc. And I'll do the same when I take the center to be B, so I don't change the length, obviously, it will still be length AB, and I will draw another arc. The arcs will meet at some point. Let me call that point C, as you can see from the picture. And then by postulate 1, I can connect A with C and B with C. Postulate 1 says that it is possible to draw a straight line from any point to any point. So A and C are any 2 points, B and C are any 2 points. By postulate 1, it is possible to connect BC and AC. So let me connect the two. Let me just write what I did so far. So first thing, construct circles or arcs, you can say. Let's say circles with center A, and B, and radius AB. and radius AB both times. By the way, to do that, to actually draw those circles, we can draw the circles by what? We can draw the circles by postulate 3. Both times by postulate 3. So this is possible to construct circles with center A and B and radius AB. It's possible by postulate 3. Okay, so the circles meet at point C. I'm underlining this because I shall make a comment at the end of the proof. The circles meet at point C. Then by postulate 1, we connect AC or produce the lines AC and BC. We construct AC and BC. Hence, we have triangle ABC. Now we need to show that AB lengthwise is the same as BC is the same as AC. Okay. Let's look at definition 15. I did mention definition 15 in part 1. Now, definition 15 is concerning circles and radii of circles with the same center. So, by definition 15, we can conclude that since I put the compass at A and I draw a circle with radius AB. So radius AB would be the same as the length AC, as both are radii of circle with center at A. So by definition 15, AB would be equal to AC. But also by definition 15, when we point the compass at B and we draw the circle with radius AB, it would mean that AB is equal to BC. It is equal to BC. So AB is equal to AC, but also AB, it is equal to BC. Therefore, we have a triangle whose all sides are equal to one another, and we are basically done with this proof. Why did I underline the circles meet at point C? Nowhere in his postulates, common notions, or definition at this point, Euclid gave a reason as to why these two circles, one with center A and one with center B, both with the same radius AB, actually must meet at some point C. So it's not clear at all. Looks like there is a need for another postulate to conclude that the two such circles must actually meet. And it doesn't seem to be accidental. It was not until actually 1920s when Herbert Hilbert actually laid the foundations of modern geometry with his famous 20 postulates. And when he did this, he certainly did fill in the gaps that Euclid was missing in some of his proofs. Nonetheless, the circles do meet actually, and it is proven that the circles do meet. It's a different story that at this point in time Euclid could not possibly furnish such proof. So we'll move on with other propositions. Certainly I'm not, as I mentioned before, I'm not going to prove them all, but I will mention what they were. So proposition, I'll just write propositions 1.2 and 1.3. I'm not going to define them, but they deal with ability to transfer lengths, deal with ability to transfer lengths. Proposition 1.4, proposition 1.4, on the other hand, is actually the first congruence postulate, side angle side. So is the first congruence scheme, actually. As you know from your early school days, SAS or side angle side. Proposition 1.5. Proposition 1.5 dealt with the base angle of isosceles triangles. So base angles of isosceles triangles, as you all know, are equal to one another. Triangle are equal. That's simply proposition 1.5. Proposition 1.6. Proposition 1.6 is the converse of proposition 1.5. What does that mean? It means that should you have, in a triangle, if you have the base angles to be equal to one another, then the triangle must be isosceles. So it's just the converse of proposition 1.5. It's just the converse of 1.5. Proposition, for example, 1.8. Proposition 1.8 is the side congruence scheme. Or proposition 1.9. Proposition 1.9. It shows you how to bisect a given angle, bisection of a given angle. Okay, and proposition 1.10 is how to bisect a line segment. Last lecture I actually mentioned that. I did bisect some angles in my drawings, and I did mention that this is possible to prove, and proposition 1.10 is really the proof of it. So bisection of a segment, of a given segment. Okay. Proposition 113. Proposition 113. I'm just going to draw the picture. I'm not going to state the entire proposition, but should you have something like this, should you have a line, and some other line falling upon it, let me call this the line AB, and then the line CD. Then the angle ABC, so this angle here. So if this picture, then the angle ABC plus the angle ABD plus this other angle plus the other angle I meant to write this as the point B, not this. The angle ABD are equal to two right angles. Two right angles. Okay. Proposition 114. Proposition 114. Is the converse of 113. Is the converse of 113. Again, what does that mean? That means the following. If the sum of two angles is two right angles, then the two lines cross each other. Loosely speaking, that is the converse statement of proposition 114. Or better yet, if the sum of the two angles, any two angles or adjacent angles, is equal to two right angles, then the line is straight. Okay, so I'm going to actually state and prove proposition 115. So I'm going to do it here. Proposition 115. It says the following. If straight lines cut one another, they make the vertical angles equal to one another. I'll explain what vertical angles are, although you should know. So let me just write this out first. If straight lines cut one another, the vertical angles are equal to one another. Okay. Proof. First, let me draw the picture. I have two lines. Let's say this is line A, B, and this is line C, D, and let's say they cut one another at the point E. We want to show that vertical angles are equal to one another. What are vertical angles? Angles that are against each other. So this angle and this angle are vertical. This angle and this angle are also vertical. So we want to show that vertical angles are equal. It'll suffice to show for one pair, then the statement is exactly the same for the other pair. Okay, so since the line AB, since line AEB and CDE, CED, I meant to say, CED are straight lines, by proposition 113, right here, we have the following. We have what? We have angle AEC, angle AEC, plus angle CEB, plus CEB so this other angle to be equal to two right angles are equal to two right angles. Okay, and what else? Similarly, we can say that the angle BED, so this other angle here, BED, plus the angle CEB, which is the same, CEB, is also equal to two right angles. Okay? Well, then what does the postulate 4 says? Postulate 4 says that all right angles are equal to one another, so it means that the right-hand side of these two equations is the same. Two right angles are equal to two right angles. Good. CEB, the angle CEB is common for both. Then by postulate 4 and by common notion 3, what does common notion 3 says? It says that if equals are subtracted from equals, then the remainders are equal. So then by postulate 4 and common notion 3, angle AEC is equal to angle BED, and they are vertical angles. Angle AEC is equal to AEC is equal to angle BED. And then we're done. That's the end of this proposition. Next one would be proposition 116. The proof of that is short and sweet as well. Well, not so short, but certainly sweet. Let's see. Proposition 116. Proposition 116. Proposition 116 tells us the following. In any triangle, if one of the sides be produced, the exterior angle is greater than either of the interior and opposite angles. I'll write that. So, in any triangle, if one of the sides be produced, meaning be extended, be produced, the exterior angle is greater than either of the interior and opposite angles. Interior and opposite angles. Okay. So, proof. I'll draw a picture first. Okay, so let's see what we mean. Let's say that I have a triangle here. Any triangle. It doesn't have to be a special triangle or anything. Okay, so let me extend one of the sides in any triangle if one of the sides be produced or extended. So let me just extend this. Then I have this exterior angle. This is the exterior angle the statement is talking about. Is greater than either of the interior and opposite angles. So so this angle is greater than any of these two. These are the interior and opposite angles. Okay, so let me just name things. Let me call this A. Let me call this B. I'll call this C. Okay. So we want to show that the angle ACD, I'll call this D. So we want to show that angle ACD is greater than either is, let me just say, greater than either BAC, or ABC, BAC, it is this angle, and or ABC. These are interior and opposite angles. Okay, ABC. So that's the A. All right, so the first thing we do is we extend, we have extended the BC to the point D. So what we do next is bisect AC at point E. So I'm going to bisect AC at point E. This is possible by what proposition? This is proposition 10. It is possible to bisect a given segment. So let's say that we did find the middle of this segment. Let me call it E. I'll write this. So bisect AC at E. This is possible by proposition 110. Okay, and then connect B and E. This is possible by postulate 1. So connect B and E. Given any 2 points, you can draw a straight line. Okay. Connect B with E. This is postulate 1. Okay, not proposition, postulate 1. And then you're going to extend BE. So then I continue to extend BE. Okay. I should say not P, but postulate 1 here. All right. And extend BE. When I extend BE, what I'll do is there I will I'll make sure that this extension, I'll take the length in this extension. I take the length EB as well. So I'll find a point F such that EB is equal to EF. so that EB is equal to EF. This is possible by proposition 3. As you can see here, proposition 1, 2, and 1, 3 deal with ability to transfer lengths. So all I'm doing is transferring the length EB in these larger segments. This is by proposition 1, 3. Okay, right? So now I'm going to consider two triangles. Triangle AEB, AEB with triangle CEF, CEF. So I'll connect the two. Okay, consider now triangle AEB, AEB and triangle CEF, CEF. Okay, so what do I have here? AE is equal to CE by construction, right? We made sure that E is the middle of AC. So AE is equal to EC. So line AE in this triangle is equal to the line EC in this other triangle. This is by construction. Okay. Next, let me call this angle 1, and I'm going to call this angle 2, not to overload the picture. Angle 1, these are vertical angles, no? So actually this is angle 2 in triangle AEB, angle 2 is equal to angle 1 in triangle CEF, and they are vertical angles. They are equal to one another by what? By the previous proposition. So by proposition 115 as being vertical angles. And the line EB in this triangle, so in triangle AB, the line EB is actually equal to the line EF, again by construction. EF by construction. We made sure that these two are equal, and that is possible by some previous proposition by construction. Okay. So all these three mean that triangle AEB is congruent to triangle CEF by what postulate, or by what proposition rather? You have side, angle, side, and that is proposition 1,4. So this means that triangle AEB is congruent to triangle CEF by proposition 1,4. Proposition 1.4. Okay, so now I have these two congruent triangles. Let me just mark them with something so you can see the ones that we're talking about. Let me make sure they blue, I guess. So this triangle is equal to or congruent to this other triangle, the blue triangles. So now in two congruent triangles, I can say what about their angles? Since these two triangles are equal, then I can say the following. Angle BAE, 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 so I can say angle BAE is equal to what angle? ECF. ECF. Why? Because they're both facing equal sides in congruent triangles. These two angles are facing these two equal sides. So angle BAE is equal to angle ECF. So where is that getting us? Clearly, angle DCA is much larger than angle ECF. So, but clearly, angle DCA, we want to show something. So angle DCA is greater than angle ECF. 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 This is actually true by common notion 5. By common notion 5. Okay. So what does that mean? That means that the angle DCA is greater than, so angle DCA is greater than angle ABC. 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 Okay. Okay. This is one of the things that we wanted to show. No? ECF. The angle ECF. ECF is the same as the angle BAC, right? Or BAE. They are equal angles. So when I say that my larger angle DCA is larger than angle ECF, angle ECF is the same as the angle BAE or BAC. So I am done with this first part here. So I shouldn't say so, but I should say similarly. So this is done. Similarly, the angle DCA is greater than angle ABC. And this is what we wanted to show. This is as far as proposition 116 is concerned. Let me move on to page 4. Lecture 3, part 2, page 4. Lecture 3, part 2, page 4. Give me a moment to mark my borders here so you can all see. Okay. So the next proposition that I want to prove, well, so we don't really spend a lot of time on these things. I will state proposition 126, that is the angle side congruence scheme. I will prove 127 and 129, and I'll state some other ones in order to get to Pythagorean theorem. So for the moment I'm just going to state proposition 126. 126. So that's the angle side congruence. The statement, it's a bit long, so bear with me. I'll say it, then I write it. If two triangles have the two angles equal to two angles, respectively, and one side equal to one side, namely that subtending one of the equal angles, they will also have the remaining sides equal to the remaining sides and the remaining angle equal to the remaining angle. That's a lot, so I'll state it, I'll draw a picture, so that at least the statement is clear. I will not prove it, I'll move on to some other ones so we don't make this extremely long. Okay, so I'll write what I said. If two triangles have the two angles equal to two angles, respectively, and one side equal to one side, namely that subtending one of the equal angles, one of the equal angles, they will also have the remaining sides. They will also have the remaining sides equal to the remaining sides and the remaining angle equal to the remaining angle, and the remaining angle equal to the remaining angle. Okay, let me just draw a picture. So well, I don't look so perfectly identical, but okay. So let's say I have triangle ABC and triangle DEF. let me call this angle 1, angle 2, angle 3, angle 4, angle 5, angle 6. Okay, so what the statement is saying is the following. If angle 2, with other words, that's what the statement is saying. If angle 2 is equal to angle 5, angle 3 is equal to angle 6, AB is equal to DE, then AC is equal to DF, BC is equal to EF, and angle 1 is equal to angle 4. Alright, if two triangles have two angles, so have two angles, these two angles equal to two angles respectively, and one side equal to one side, namely that subtending one of the equal angles. So this is a pair of equal angles, and this is a side subtending one of those equal angles. They will also have the remaining sides equal, meaning these two will be equal and these two sides will be equal, and the remaining angle equal, meaning angle 1 and angle 4. So angle 3 and angle 6 equal, 2 and 5 equal. This is one of the sides subtending one of the equal angles, so these are the givens. These are the givens. If this, then the remaining sides are equal, so AC is equal to DF, BC is equal to EF, and that last angle is equal to what remains on the other triangle as well. I'm not going to prove this, but we shall use it. This is otherwise known in modern geometry as angle side, modern Euclidean geometry, that is. Okay, so I'll move on to proposition 127. Let me see. So I'll state 127, I'll prove 129, I'll state some more, and then we'll stop for the part 2 and move on to part 3 with the Pythagorean theorem. Okay. Proposition 127 says the following. No proof here. I believe proof is in the book. Proposition 127, again, statement, no proof. It says the following. If a straight line falling on two straight lines make the alternate angles equal to one another, then the straight lines will be parallel. Let me write that, draw a picture, and explain the picture according to the statement, and then move on. So, if a straight line falling on two straight lines makes the makes the alternate angles equal, to one another, then the straight lines will be parallel. Then the straight lines will be parallel. Okay. It says the following. So you have a straight line falling on two other straight lines. Makes the alternate angles equal. These are alternate angles. So let me call this angle 1, angle 2. Then the two straight lines will be parallel. So let me call this line 1, line 2, line 3. So the statement says the following. If under this condition angle 1 is equal to angle 2, as you can see in the figure, we mean here alternate angles, then L2 is parallel to line L3. This is proposition 127. All right, I'll state 129, prove 132, and then call it a day. Call it a day with part 2. Okay, proposition 129. We need to refer to all of those again for the final proof of Pythagorean theorem, which is the finale of chapter 2. Okay, so 129 says the following. A straight line falling on parallel straight lines makes the alternate angles equal to one another. This is in some sense the opposite statement, or the converse of proposition 127. So let me just write that. If a straight line falling on a parallel, on parallel straight lines, I shouldn't say if at all. I should say a straight line falling on parallel straight lines makes the alternate angles equal to one another. Angles equal to one another. Keep in mind, well, it's the same figure as this one. Proposition 129 and 127 are not saying the same thing. This is saying that if you have a line falling on two others in such a way that the alternate angles are equal to one another, then the lines are parallel. So if alternate angles are equal, then lines are parallel. This is saying if the lines are parallel, then the alternate angles are equal. That's what 129 is saying, and it is referring the same figure as proposition 127. So same figure as proposition 127. I repeat, they're not saying the same thing. Okay, proposition 132. Proposition 132. The proof of this is not long at all, so I shall prove that. Then state 141, 146, and finish part 2. Okay. Proposition 132 says the following. In any triangle, the three interior angles are equal to two right angles. This is what we know to be the sum of interior angles in any triangle is 180 degrees. That's how we know it in modern days. Okay, so I'll write that. In any triangle, the three interior angles are equal to two right angles. Okay. I'll draw a picture and we'll prove it. Okay, so the first thing we do, we are going to consider some arbitrary triangle, ABC. Show proof. So given is the triangle ABC. Okay. Let me call this interior angle 1, interior angle 2, and interior angle 3. Okay, so we are going to first, so given is triangle ABC. Extend BC to point D. So I'm going to extend this, let me call this point D. And here at point C, I'm going to draw CE parallel to AB. This is certainly possible by previous proposition and definitions and whatnot. So here I'm going to draw the line CE parallel to AB, to point D, and draw CE parallel to AB. Now, by proposition 129, I'll do some more labeling actually. Let me call this angle 4. Let me call this angle 5. Okay, so by proposition 129, angle 1 is equal to angle 4. They are what? These two are alternating angles. So by proposition 129, these are the two parallel lines, then a third one falling upon them, then the alternating angles are equal to one another. 1 and 4 are alternating angles. So angle 1 is equal to angle 4. Also, angle 2 is equal to angle 5. So angle 2 is equal to angle 5. Why is that? Let me continue here. 2 and 5, keep in mind we're still talking about these two parallel lines, A, B, and C. 2 and 5 are actually two corresponding angles of parallel lines, and they are equal to one another. So they are two corresponding. We're talking about the line AB parallel to CE cut by the line BCD. Two corresponding angles of the parallel lines. Okay. So we have what? So we have angle 1 plus angle 2 plus angle 3 to be equal to what? I just said before that angle 1 is equal to angle 4, so instead of angle 1, I'll write angle 4. Okay? We just said that angle 2 is equal to angle 5, so instead of angle 2, I'll write angle 5. And angle 3 is common. So 1 is equal to 4, 2 is equal to 5, and 3 is equal to 3. Well, 3 plus 4 plus 5 is actually equal to what? To 2 right angles. 2 right angles by previous propositions. 1 plus 2 plus 3 are the interior angles of a triangle, and they are equal to 3 plus 4 plus 5, and the sum of the 3 forms this straight line BD. And we know from one of the propositions that I mentioned before that the sum is 2 right angles. So since these 3 angles actually form this straight line, since these formed the straight line BCD. The straight line BCD. Okay, so that's the end of this. 2 more important propositions, just state them, and we are done with this part. So proposition 1.41, it says the following. Before any of these propositions, when we talked about definitions, one of those definitions was what a rectangle is, what a parallelogram is. I mentioned that in the previous part. So proposition 141 says the following. If a parallelogram at this point is defined very well what it is. So if a parallelogram have the same base has the same base with a triangle, and is in the same parallels, I'll draw a picture so I can show you what I mean by that. Is in the same parallels. Then the parallelogram is double of the triangle area-wise. The area of the parallelogram is double that of the triangle. The parallelogram is double the triangle area-wise. Alright, so just let me draw a picture. Let's say that I have this parallelogram here. talking about is this. So, as you can see, here is my parallelogram. I call it A, B, C, D, E. So the parallelogram A, B, C, D has the same base, the base AB, as the triangle ABE. And they are in the same parallels. See, they both lie in these two parallels. If that's the case, the area of the parallelogram is double the area of the triangle. In fact, this is the modern formula for the area of a triangle. Area of a triangle is equal to half base times height, no? That's to say that a triangle is half the area of the parallelogram in question, or the parallelogram is double the area of the triangle in question, should they be sharing the same base and lie in the same parallels. All right, the last proposition for this part. Last proposition would be proposition 146. It states the following: it is possible, it is possible to construct a square upon a given line. It is possible to construct a square upon a given line. So if you are given some line AB, it is possible to construct a square on the top of that line. That is not obvious at all, and surely requires a proof. Anyway, next proposition, which is proposition 47, is nothing other than the Pythagorean theorem, and that would be part 3 of lecture 3. See you in a minute.